good afternoon, and thank you for making the time to join us for this webinar about cracking the trickiest concepts in secondary maths. We are delighted to have Pete Mattock, who will share some high-impact approaches and some classroom strategies. Pete is a specialist leader of education and an accredited maths professional development lead. He has been teaching and leading maths for over years. He is also an author and part of the first cohort of specialists trained in the mastery approaches by the National Center for Excellence in the Teaching of Mathematics. I will hand over to Pete in a moment, but just a bit of housekeeping before we begin. There's a Q&A in the bottom right corner of your screens where you can submit questions throughout the session, and we'll leave enough time to address these at the end, so please do make use of that. I believe the chat box is disabled, but if there are issues with audio or video, you can pop those in the Q&A box as well, and we'll try to address everything. We will also be distributing a recording of this webinar after the session has ended. So I'll now pass the mic off for Pete to get started.
Brilliant. Thanks, Bella, and welcome to everybody who is attending today. And yes, I am Pete Mattock, and I'm here to talk today about cracking tricky concepts in secondary maths, particularly at GCSE and GCSE level maths. As Bella said, I've been teaching maths now for a very long time, nearly 20 years, until last summer, when I left the classroom in order to become Twinkle's National Education Lead in Secondary Maths, which is the role I take now. And yes, I've done quite a few bits, as Bella said, across that, so I won't go over it, but I've been very lucky in my career to have a number of opportunities to work with some fantastic people and to develop my skills in teaching. And so hopefully I will pass some of that on to you today. So let's get into cracking the tricky concepts. And my advice today is going to boil down broadly to three things. And that is to focus on structure. The trickiest concepts, those that we want our high attainers to really grasp and move on with, we need them to understand and focus on structure. Yeah. Now, personally, I like all maths learners to understand and focus on structure, but at certain grades and at certain levels at GCSE, you can very often get by with a more procedural knowledge, shall we say. A more procedural knowledge will get you up into those sort of low to mid-range grades. But for the top end grades where we find these tricky concepts, students really need to understand and utilize structure. So I'm going to talk a little bit about that. An important aspect of this is to model the problem solving rather than the problem. So with these tricky concepts, they often present, certainly in examination questions, as quite developed questions that are worth multiple marks. And while you can quite easily model an approach to a particular question or a particular problem, what really benefits learners is if you also at the same time model the problem-solving approach that you are taking. So we're going to see some specific examples of that and what that looks like. And then really important, again, it comes back to bullet point one a little bit, but connecting concepts and representations. For these trickier concepts, being able to connect them to other concepts that we've studied or other representations of that concept can be really powerful in unlocking learners' ability to work with them on those harder top-end sort of questions. So let's have a look at the first one. So here is a typical sort of GCSE question example involving vectors. And this is definitely the sort of question that is going to discriminate between those students at grade 7 and those students that are, or grade 7 or above, and those students that are perhaps not going to achieve that in the time that we have with them. And I've answered part A already because it has a bearing on part B, but part B is the tricky one there. Yeah, you will find kids that aren't going to get those top end grades that will be able to answer part A of that. But part B is often the one that students find a little bit more difficult. And that is being able to justify whether the line ADE is a straight line. It certainly doesn't look like a straight line, but whether it is a straight line or not, or variations on that, is AD parallel to OE or something like that. And when I say focus on structure here, what I mean is don't focus too much initially with something like this on the utilization of vectors. Yeah, we are going to use vectors, but don't focus initially so much on the utilization of vectors. Take it back a step and focus on the structure. What does it mean for a line to be straight? How can we actually recognize and show that lines are straight, even without any vector ideas or anything like that? How can we show that lines are straight? And we have other approaches in mathematics to doing that. We might talk about gradient, and vector has very strong links to gradient. That you can see how this ties to connecting concepts and representations as well. But you know, gradient can show us lines are straight. Two line segments meeting at 180 degrees can show us lines are straight. Importantly, what does it mean for a line to be straight? It means that the segments have the same direction. If you're talking about two line segments coming together to form a line, that line is straight if they move in the same direction. And vectors is just one of the ways of telling us what direction a line segment moves in. And so when we approach it like that, it then becomes like, okay, well, let's find out something about the direction of these lines. The magnitude bit doesn't matter. Let's find something about the direction of these lines. Let's find something about the direction of line segment AD. Well, we already know that because we did that in part A. Great. And let's find something about the direction of the line segment DE. And we could do that. I'm not going to do the maths here. I could because I've got a little pen and I could do the maths here, but I'm not going to. But actually, I mean, privately, I can see that it definitely can't be because I can see that it's OE that is parallel to that. But we'll come to that. We can come to that later with students. Let's find something about the direction of the line segment DE and, negative a half C plus OE, which we worked out before. And we can show kids there how the reason why A part I and A part II were there in that question, because they help us to answer part B. And once we've got those two directions, okay, now we know something about those directions. How are we going to tell if they're pointing in the same direction or not? And that becomes the bit where we're actually utilizing and comparing the vectors. But if we start with a question like that, by focusing on the structure, what does it mean for a line to be straight? How do we decide whether two line segments will come together to form a straight line? And different ways and the fundamental structure of how that works, both line segments pointing in the same direction, then it's much easier to justify using vectors for this, as well as being able to say, yeah, we could use gradient. We could get if the diagram was to scale, we could get a protractor out and do it as well. Okay. As another example, again, a tricky concept for many students is the graphing of inequalities. Many of them will learn to do this in a very procedural way, but they'll make mistakes. Misconceptions and errors abound in this, in my experience, for working with students. But again, what we've got there is four inequalities. Let's just focus on the structure of each of those. What does it mean for that y greater than 1? What does that actually mean in terms of positions on that space? We've got a two-dimensional space here. What does it mean for positions on that space where y is greater than 1? And obviously for us, and what we can be talking to kids about and getting kids to discuss is, well, it means they must be above a certain point in that picture. Yeah. And the point in that picture, of course, is the line y equals 1. And setting that boundary allows us to show where things are above or below. And then moving on to, we probably move on to the one that x is greater than or equal to 4 next, before we do the other ones both involving x and y. But what does it mean to have x values in this space that are greater than 4? What does that look like? Focus on that structure. What does it mean for that to happen in this two-dimensional space? and then x plus y is less than 10. Okay, well, what does that actually mean in terms of points on this space for which that is true? Yeah, it's very easy to just break this down, or to, very easy for a teacher to just break this down and do it procedurally and say, replace all the inequality signs with equal signs, draw the lines, and then do the region. But actually, that can, kids can struggle then. They might draw the lines, but they can struggle then to see the region and why the region is what it is. Whereas if we focus on the structure, what does it mean for this to be, for y to be greater than 2x minus 10? What are points? Where are the points in this space for which that happens? And focus on that structure, then actually those lines, and we can talk about the technicalities of dash lines and full lines and why that is. That's just a notation thing at the end of the day. But those lines, as and the reason for those lines appearing becomes much more apparent. And then we can sort of target that region that is bounded by those four lines. So when I say focus on structure here, that's the sort of thing I mean. I mean, get back to the fundamentals of what do these things mean? What does it mean for a line to be straight? What's the underpinning structure that determines whether a line is straight or not? What's the underpinning structure behind what these things are in terms of these inequalities? What it means to have a coordinate with a y value greater than 1, or x and y values that add to 10, or a y value that is greater than 2x minus 10. And if we get back to that structure and start giving kids insight and opportunities to play with those structures and make sense of those structures, they're much more set up to tackle these sort of harder multi-mark questions. So that was the first one. Now let's go into the second one. Model the problem solving, not the problem. Okay. Again, we've got a fairly standard sort of question that would appear on a GCSE exam here. Excuse me a second. My dog has just decided to join me, and that's why my door's burst open. We've got a fairly standard circle theorems question here. Again, the sort of question that would likely discriminate between those sort of candidates that are going to get to, in England, at least grade 7 or better. There aren't many candidates that are going to get grade 7 that are not going to work themselves all the way through this question or problem. And it would be very easy here for me to look at this particular question and say, okay, well, I know this is 50, so therefore I know this is 100, and therefore this and this. But actually, what I need to be doing here is unpacking that thought process about how I know that's 100, how I know the 40s and all the rest of it. So my introduction into a problem like this, if I'm going to model the problem solving, is I'm going to look at it and go, okay, well, I can see a circle with some tangents, some radii, and a triangle. So immediately I'm thinking circle theorems is going to be the area of maths that I need to be considering. What circle theorems can I see that might be applicable here? Well, I've got a tangent and I've got a radius, so I might be using the fact that they meet at right angles. I've got a triangle with a point on the tangent and two of the points on the circumference, which brings to mind the alternate segment theorem. So I might be looking to see what the alternate segment theorem can tell me about this scenario. I can see a triangle with two radii formed here, and that's telling me it's an isosceles triangle, and it's also giving me something about angle at the center being twice angle at the edge. So I feel like those circle theorems are going to be the key ones in this. One or more of those are going to be the key ones in this, along with the isosceles triangle. And actually unpacking your thought process about how you look at that and recognize A, that it's a circle theorems question, which you'd expect most kids at that level to do. But A, that it's a circle theorem question, and B, which circle theorems are going to be important here and how I recognize which circle theorems are going to be important here. is important for students then to be able to take that and apply it to diagrams that they haven't seen. Because let's face it, you're never going to be able to show every possible circle theorem diagram. And certainly in England, examiners are tasked to try and find novel ways to test this sort of stuff. So likely scenario is kids are going to be walking into exams, seeing a circle theorem question on a diagram that isn't exactly the same as any that they've seen before. Might be similar, but not exactly the same. So being able to get them to go through that process and modeling that process as an expert of how do I look at this? What information for those students that are going to try and achieve those top grades in order to tackle those tricky concepts. Another example here, and again, if you're experienced teacher of maths, you will look at that and know that it's about right angle, Pythagoras, and trigonometry, and importantly, know that it doesn't require any non-right angled trigonometry. But I need to communicate that to pupils, not just dive in and solve this particular problem. Yeah. So I'm going to be looking at something like this and say, okay, well, what I see here is some right angle triangles straight the way. There's a right angle triangle here and here, and that involved that I'm getting information about that triangle, about sides and also about angles. So immediately I'm thinking trigonometry because I've got sides and angles. I'm also seeing that a lot of these lines are either horizontal or vertical and therefore at right angles to each other, or they are connecting the ends of horizontal and vertical lines. So this is making me think that I should be able to tackle this problem and right angle Pythagoras if I need to bring some Pythagoras in. But I'm feeling like right angle trigonometry is where I need to be with this problem. So if I'm going to be doing some right angle trigonometry, I need to be thinking about where there might be some other right angle triangles in this scenario. And I can create right angle triangles wherever I split a rectangle into two. So where are my rectangles? Well, ABDE is a rectangle, and that's the crucial one in this case, as we know. I wouldn't lead that with students, but that is the crucial one in this case because it's what's going to allow us to find AE. I can create right angle triangles by splitting the rectangle of the base in half, should I wish, diagonally, or I shouldn't say diagonally, really. Oh, no, it is diagonal, it's fine. Or this back rectangle, I might be able to create two right angle triangles there. Let's see which right angle triangles, other than the obvious ones, A, B, C, and D, E, F, let's see which right angle triangles are going to be useful for this problem. Find the angle the line AE makes with the plane. So have I got that line AE? Right. So I feel like this right angle triangle here is going to be a useful right angle triangle. And that's what I mean by model the problem solving, not the problem. We've got to give students insight into an expert's thought process in that scenario. The thinking that we do almost automatically that just comes into our head needs to be considered and explicitly unpacked for students so that they've got access to that same thinking that they can then take into unknown problems. So this is what I mean when I talk about model the problem solving, not the problem. And then the final one for me, connecting representations and concepts. So again, we've got here a tricky concept for most students. Many students struggle with the idea of functions and the use of functions and function notation, particularly when it comes to composite and inverse functions. So let's look to connect this to things that students have studied in the past. So if I'm doing a relatively simple thing like evaluating a function for a certain input, in this case, x equals 2, let's show that f2 equals 3 times 2 plus 2, which is 8. But let's show it alongside a function machine. And I know that function machines are not a long-term useful representation for functions, because if you've got multiple inputs, multiple values of x, a function machine is not going to handle this. But when I'm building the concept for learners, starting with something like this and connecting it to a function machine can be really powerful for them to see, okay, actually, this is just a new representation of something that I'm already very comfortable with. Instead of seeing it as a function machine, I'm seeing it as, F operating on X, but actually it can operate on anything, just like I can take any input into the function machine. The other thing I tie it to is substitution that they might have seen before, particularly in this case for f of x, straight line substitution. But, depending on the function, it's about more general substitution. We've done this before, finding one value when we're given a value of x, finding a value of y or whatever it might be when we're given a value of x. And we know that that's just substitution. Well, actually, the same thing's going on here. Now, where students probably have never done this with those previous two representations is to substitute algebraic expressions. And I would always do this with students before I just go straight for let's compose these functions. Actually just say, okay, well, if we're used to substituting values in, and we can see how substituting the value of 2 into this function is the same as using 2 as the input into this function machine, is the same as substituting 2 into this formula. Well, why can't we put algebraic expressions in as our input, as our substitution? And it looks like that here. It looks like that there. And it looks like that there. It's no different. It might be something students haven't seen before, but it's absolutely no different. Fundamentally, it doesn't affect the process that students have to go through, no matter which representation it appears in. And showing them that can be really powerful. Showing them those connections can be really, really powerful. And then, of course, I've done a bit of that. We can get into composing those functions. Okay. Let's take g of x and use that as our input. And it looks like that in this function machine. It look in that function red notation. It looks like that in the function machine. And it's just me asking you that if I was talking about a substitution. There's no difference across any of those three. And it makes it much more comfortable for students because they can connect it to what they've seen before. It connects across those three different representations of what is fundamentally the same idea, the idea of substituting. And then when we move into inverse functions, and I played with inverse functions in different ways over my career, and I have to say the way that I absolutely 100% prefer is utilizing of this. And this is just something that has to be taught to students. The idea that if we apply a function to its inverse, we get back to our original input. We can use a function machine to do that. Yeah, I haven't put that in the slides, but we can use a function machine to do that. If we've applied a function to an inverse function, we undo the steps basically, and we get back to the input we started with. And what that allows us to do is say, okay, well, let's take this f of x then and do what we did before on the previous slide. Just substitute f minus 1 of x in. Now, we don't know what f minus 1 of x is yet, but that's fine. Yeah, we can still do that. And then we can rearrange, just like we would if we were solving an equation, to solve for f minus 1 of x. And I find that approach much preferable to the approach that others might take, which is to rewrite f of x with y and then to rearrange to get x in terms of y and then just magically swap those variables over because we want f of x rather than f of y. But, those letters just swap around. It doesn't connect with anything I've seen before, whereas it connects with that. And then with the function machine, you've got that beautiful representation of exactly what happens. And again, we can connect that to equation solving. We can connect that to writing inverse function machines if students have experienced that before. There's a lovely way there to connect those representations and those concepts together. Another example, this is one of my favorite ones, proof, anything with proof. Typically, proofs at this level are going to be linked to one of two areas, either sequences or inequalities. Typically, students are either asked to prove something is always positive or always negative using completing the square, so linked to completing the square and inequality, or they might be asked to prove something like this, that the square of any positive integer isn't a multiple of 3. Possibly slightly more likely for an A-level student than a GCSE student to have this phrased in this way, but it's a lovely thing we can use to teach the idea of proof. And when I'm approaching something like this, I will always connect it to sequences. So let's just take some numbers. Yeah, there we are. And we need to look at those numbers that are not multiples of 3, but I'm going to start with looking at those numbers which are, because if we take out the ones that are, we'll be left with the ones that aren't. So here are the multiples of 3. And if we take those out, and obviously I'm doing this with some very clever PowerPoint animation, but if I was just writing this board, I'd just be rubbing them out and rewriting them on the right-hand side. If we take those out, well, those form a sequence. Those form a sequence that we know quite a lot of and quite a lot about. They form the sequence with the nth term 3n. Okay. Oh, 3n, that's interesting. Let's form some other sequences based on 3n. Let's take these numbers next and pull those out. Now, they're part of the group that isn't a multiple of 3, but they do go up in 3s. Let's pull those out. And make a sequence out of those. That's the sequence 3n minus 1. And again, this ties to stuff that kids who are working at this level will definitely have seen before, being able to take a linear sequence and find its nth term. And then that leaves us with these numbers, which also, not surprisingly, go up in 3s. So let's pull those out. And let's just treat them as a little sequence. And this is the sequence, of course, 3n minus 2. And so if we now return to the proof, we're saying, well, what we've got here is two categories of numbers that aren't a multiple of 3. They're either in the sequence 3n minus 1 or they're in the sequence 3n minus 2. So now let's try going and proving that if we square either of those, that leaves a remainder of 1 on division by 3. And from there, the proof follows quite simply. We take 3n minus 1 as the nth term, we square it, and we can show that that can be written as a multiple of 3. And then we take 3n minus 2 and we square it, and we show that that, with a little tweak, can be written as a multiple of 3 as well. Yeah, but with what we're tying there is we're tying together the representation of numbers that are or are not a multiple of 3 with the previous concept that the students have studied around linear sequences. And we do that with all sorts of things. You know, if you're proving about 2-digit numbers, you'll be tying it to 10x plus y or something like that. If you're proving something about even numbers or odd numbers, you'll be using 2n minus 1, 2n plus 1. But rather than just magically introducing those things, for me, it's much better and it makes it much clearer to start with students to say, okay, this proof is about even numbers. So let's look at some even numbers and write down what we know about even numbers. We know they form a linear sequence. The linear sequence is 2n. And then, right, okay, so if we're going to prove something about even numbers, we're going to prove something about this expression 2n. Okay. My last one, which I have to do because it's probably my favorite representation in all of mathematics, show that the difference between two squares of any two numbers is equal to the product. Now, difference of two squares is something that kids most of the time will recognize, certainly the ones at this level, but I always show kids that working at this level this because they need to see this connection. So this is what that whole spiel boils down to. The difference between the squares of any two numbers is equal to the product of the sum of the numbers, x plus y, and the difference of the two numbers, x minus y. But I never let kids work with that. without showing them it pictorially and showing this representation, because it just unpacks exactly what that means and exactly what that looks like. So here I have an x square. It's a square that's x by x. And here I have a y square superimposed on it, which is y by y. And so the remaining blue area there is the difference between those two squares. Yeah, we've got the x square and the y square. So if we remove this y square from this x square, that blue area is what's left. It is x squared minus y squared. And so we've got x minus y and x minus y there. And you can see I've done some clever animation. I've split that area into two chunks. This chunk here, which is x minus y by y. This chunk here, which is x minus y by x. And if I simply rotate that around, I then have the area that's left being an x minus y by x plus y area. Now, I will actually show that almost certainly using dynamic geometry on GeoGebra or Desmos or something like that. I couldn't get the embedding to work on the PowerPoint slide, which is why I've animated it for you on the PowerPoint slide. But there are some great animations for that in GeoGebra, Desmos, places like that, where you can use the dynamic geometry to actually show that rotating around. And even though that's possibly not the trickiest concept that I've shown you today, it is a wonderful way of connecting algebraic and pictorial representations that I just couldn't finish the session today without showing you. So hopefully that has given you some insight into how I approach and how I found works approaching the teaching of those trickiest maths concepts, those questions and the concepts that the questions are based on, that are really going to discriminate between those top end candidates, the grade 7, grade 8, grade 9 candidates, and sort of the things that you might want to consider in your pedagogy and in your practice to make sure that students can handle those as well as you can when you come to see them. The little plug, as always, because the publisher makes me do that. But if you want to know more about concepts and how to approach them, then actually the book on the right is the one you want to be looking at. That contains, as far as I can tell, every school level maths concept that we teach at primary or secondary school, literally every bit of maths that we teach. It includes a lot of this in terms of what is the fundamental structure that underpins it. It includes representations we might use to help teach it. It includes questions we might ask and ways we might approach it. It's a huge book, but it contains, as far as I can see, literally everything that anybody would need to teach any maths concept at certainly upper primary at least, or secondary. But it goes right back into basic number and place value and things like that. If you are particularly interested in representations and structure, then the book on the left is the one that I would recommend. That is my first book, Visible Maths, literally using representation and structure to enhance maths teaching in schools. So it focuses a lot in number and algebra in particular, and how we can use supporting manipulatives and supporting representations to support all learners from the lowest to the highest in making sense of those mathematical ideas. Fingers crossed that's been useful for you. If it's not, I'm sorry to have wasted 35 minutes of your time, but if you take one thing away from it, then it's not a waste. And that is the end of our webinar. So I will pass back to Bella and we will look at questions. If you've not yet written your questions, then please do so now. Pop them in the Q&A.
Oh, that was so great. Just while we're waiting for people to gather their thoughts and pop those questions in, I had some for you, if that's okay.
Of course.
I really liked the linear sequences example, and I was wondering, when you are using multiple representations to connect concepts, how do you avoid cognitive overload with your students?
Yeah, absolutely. So and I'm sure people are looking at, 3 representations at once on the screen for those functions, and it can be an issue that you've got to manage. I think the key thing there is, and I alluded to that in the presentation, is the other representations have got to be really secure. You know, if kids have never seen function machines before, then you can't use function machines to help make sense of function notation, because all you're doing is compounding one thing they haven't seen before with another thing they haven't seen before. And that is definitely going to lead to cognitive overload. So whether you test that in prerequisite knowledge before you start teaching it to make sure kids are familiar with it, or activate it as part of your prior knowledge activation part of the lesson, whether you, because you've taught the class for a number of years, you know it's something they've seen before, but you've got to be absolutely 100% sure that kids have seen that concept being treated in that way. And if they've not seen that concept being treated in that way before, then you are likely to overload them by including it. So yeah, only do it if you're absolutely sure that they've seen that representation or that way of thinking with around a concept previously, because it's that then that you're trying to build on, and you can't build on it if it's not secure.
That makes a lot of sense. I'm going to keep going since the chat is quite quiet. But I was also
Lovely.
wondering, how do you shift the mindset, or like what are the best verbal cues you found for having students focus on modeling the problem solving instead of the problem?
Yeah, so John Mason writes a lot about this actually. He writes about metacognitive, no, not metacognitive. It was Colin Foster that talks about um, modeling the problem solving, not the problem. I can't remember what he calls them now. But anyway, he definitely wrote a lot about it. If I can remember what he calls them before I finish this little spiel, I will. But what it's about is starting by asking very explicit questions and sort of pairing that back to then asking students to think about what you're going to ask them. So I'll give a practical example of this, with not trickiest concepts actually, but a practical example of this. What I used to, so when I was teaching proportion ratio, things like that, a representation I used to use a lot was a bar model. And so when I would, set students off on work, guided practice, things like that, one of the things I would say to them is, if you ask me for help, the first thing I'm going to say is, where is your bar model? And if you haven't drawn a bar model, I'm not going to give you any more guidance until you've drawn one. Even if it's not right, I don't mind, just draw one. And so that was very explicit. I want you to draw a bar model if you're struggling to do this. But then a little way down the line, I would change that to, what am I not going to help you until you've drawn? So that kids actually internalize that and say, oh, yes, I've got. And then eventually it would just become, and what am I going to say to you now? And kids would tell me, you're going to say to us that we need to draw a bar model first before we ask for any more help. And that gets them to internalize that support, internalize that structure. And you can do the same thing with all of those things. With the circle theorems one, you can start by saying, okay, I'm thinking about this, and then you can, after a little while, you can turn it around on students. The next lesson or the lesson afterwards, or the next time you bump into circle theorems, whatever, you can turn it around on students and say, okay, so what am I thinking now? Tell me what I'm probably thinking now, looking at this problem. And if you model problem solving regularly like that, you stop giving the prompts and you start asking them for the prompts, and then eventually it becomes internalizing their support. That is definitely a phrase John Mason did use. It wasn't what he called it, but he definitely did use it, internalizing the support.
Yeah, that repetition is so helpful. I think I still remember teachers, like phrases that the teachers in the past I had would use all the time. And it still pops in my head now.
Lovely. Do we have any
And then I
more
was also
questions?
wondering
Oh, go on then.
what tips. Oh, sorry, I'm still going because everybody's quite quiet. You guys don't have to be shy. Pop them in there in the Q&A box. I saw somebody commented that the chat is disabled, but I messaged just to say you can pop it into the Q&A and we should be able to see it.
Do people
But
know
what
where the
tips did
Q&A are? Do people know how to access the Q&A on Zoom?
it should be in the middle of their screens, but I'm not sure if they're having issues. The person who messaged did write in the Q&A box.
Okay, lovely. That's fine.
So hopefully it's there. But what tips do you have for upskilling your team about how to improve the teaching of these concepts?
Right. Yeah. So, I mean, obviously, if you're here on the webinar, you might be disseminating this out to your team, or you might, you might be responsible for this as part of your team. You might not be. You might just be an interested teacher, but if you're coming along to PD, you probably want to be using that to influence the direction. What I would say is, for teachers to change their practice, typically they've got to be convinced that something is working or is going to work. So if you can take this back into your school and into your classroom and show that it works, try it in your own classroom, show through data or through pupil voice or whatever, qualitative, quantitative approaches, that actually this is having impact on student confidence, it's having impact on student outcomes, hopefully. But student confidence in approaching these sorts of things, that's definitely a top tip. Teachers, particularly teachers that are a bit more experienced, are very reticent to change a practice until they're sure it's beneficial. The other thing I would do is, certainly if I was doing this in a department meeting as a head of department or leading on developing this sort of thing in teaching, would be to actually get teachers to sort of tackle some of those problems themselves, some of those tricky maths topics. Send a couple of hard exam questions out in advance of a meeting and get them to do it, and also reflect on how they would teach it, and then compare and contrast. Get teachers in. I love teachers doing maths in department meetings and things like that, because it provides opportunities for comparing, contrasting both approaches, but also then the pedagogy that underpins those approaches. Getting them talking about how would you approach the modeling of that, the teaching of that, and how would I approach it differently, and can we refine what we're doing? Because for most teachers, again, particularly experienced teachers, refining something is a lot more accessible than completely changing something.
And also to see if it matches probably as well. If the technique they're using to solve a problem is also the same approach that they're actually teaching, I'm guessing.
I mean, yeah, certainly you would hope so.
Yeah.
Sometimes expert maths teachers take shortcuts that they wouldn't necessarily suggest to pupils until pupils have got a bit more experience of it.
Yeah.
But of course, that then becomes part of the discussion around the pedagogy. Would you actually teach it like that? I mean, I I will say that I would never phrase it like that, because it implies judgment. So I'd never say to my, would you actually teach it like that? Because it implies judgment. But how does the way you've approached solving the problem relate to how you would teach the solving of problems like this? And can we draw out any general themes about how we would approach problems like this, no matter what it looked like? Because they're the behaviors and skills that we need to make sure students are actually picking up.
Yeah. Well, very lovely. Thank you very much for joining us and for your participation. And Pete, thank you so much for putting together this session and sharing your insights with us. We will be sending out a recording of this session. So everybody who's here, please watch out in your inbox for that. And we also have a small request, which is to help us to be able to continue to host and facilitate sessions like this. We do need some input from you. So there will be a short survey in your browser directly after the webinar ends. And we'd really appreciate it if you could just take a couple seconds to provide your feedback. But thank you again. And Pete, thank you so much. You're so interactive, enthusiastic, and a joy to listen to. Thank you.
Thank you very much. Thank you very much, everybody, for coming. Hi, Gianluca. I can see you still there. Gianluca was one of my trainees.
Oh, no way.
And
That's so
he was
nice.
told me coming along to this, so I wanted to give him a shout out while he's still in the room.
Oh, that's lovely. Well, thank you very, very much.